Okay, so we'll start off by looking at some of the forces on an ankle. Okay, it's quite interesting. So what we'll look at is, suppose a person stands on one foot on tiptoe. So you're standing like that, on tiptoe, and let's look at the forces. Okay, so this is the foot you're standing on. There's your weight. Your weight is m times g. M is your mass, g is the acceleration due to gravity. Okay, and so the force on this toe, since is balancing your weight, so this is mg. That's equal to your weight. All right, so now what we are interested in is what are the forces here on this ankle and what are the forces on the tendon. And what I'll show you in a second is this force is 3 times mg. So the force on that tendon is 3 times your body weight. The force on this ankle joint is 4 mg, is 4 times your body weight. Okay? And of course, so this is just standing on a toe like that. What happens if you skip like this on that one toe? The forces will go up. Okay? They can go up to 5 to 7 times. Okay? So let's see how these large forces arise. Okay? So here's a model of this ankle. Okay, there's the ankle. There's the force that the ground exerts on the toe, which is equal to your weight. Okay. This is the force that the ankle, this bone exerts on the ankle joint, and this is the force on the tendon. Okay. And here's how the calculations go. All right, so if you take this as the pivot point, what this force is doing is it's trying to turn the ankle clockwise about that pivot point. And what is balancing is this force in the tendon that's trying to rotate your ankle counterclockwise. So if you're standing there at rest like that, then that means this clockwise torque is being balanced by the counterclockwise torque. Okay? And if you take this as the pivot point, then your weight is trying to rotate the ankle clockwise, and the force on the tendon is rotating it counterclockwise about this point. So those are balanced. Okay, so that's how we'll calculate the forces. Okay. Again, what we want to show you is that this force is 4 times your body weight, and this force is 3 times your body weight. Okay. So the force on the toe is equal to your body weight. The force on your toe. Okay. Now, so in this diagram, if this angle is theta, then it turns out that this angle is theta. Okay, so if you have done a little geometry, you can figure that out. This angle is theta, and this angle is theta. Okay, so for this guy, okay, so this force can be broken up into a force like that and a force like this. This force has no torque about that point. Only this force has a torque. And so this force on the toe, force on the toe times cosine theta, force on the toe times cosine theta, times the moment arm, which is 15 centimeters times 15 centimeters, is equal to the force on the tendon times cosine theta. So this force can also be broken up into a force like that and that. This component has no torque, only this component has torque. It's force times cosine theta, tendon force times cosine theta, times the moment term, phi. The cosine theta cancels. The force on the tendon is 15 divided by phi, 3 times the force on the toe. The force on the toe is your weight. So what this equation is saying is the force on your tendon when you stand on tippy toe on one foot is 3 times the force on your Achilles tendon is 3 times your body weight. Okay? And now let's calculate the force on the ankle joint. Okay? Now we'll calculate, so for this part we calculated the torques about, this was the pivot point. For the second calculation, this will be our pivot point. Okay? Now, this force is rotating your ankle clockwise. This force is rotating it counterclockwise. Okay? Again, you don't have to know the details of the calculation, but you do have to know the results. Okay? All right, so the force on the tendon, again, this component of the force does not have any torque, only this component of the force has a torque. So this is F cosine theta, the tendon force times cosine theta, and the moment arm about this point is 20 centimeters times 20 centimeters.
Just to clarify, the force on the tendon moves counterclockwise and the force on the toe moves clockwise?
So for this calculation, when this is the pivot point, this force will try and rotate this ankle counterclockwise.
Okay, and then the toe would
The-
try to move?
Well, no, that's the pivot point.
Oh, the toe's pivot point, okay.
Yeah, this force will turn the ankle clockwise.
Oh, the force on the sole of the foot?
No, the force on this bone from the,
The ankle bone,
yeah.
okay.
So the counterclockwise torque is being balanced by the clockwise torque when the object is at rest, when your ankle is at rest. Yep.
Maybe I'm the only one that doesn't understand, but what does theta mean? Like, are you talking about like right angles, or is that what does theta mean?
Theta is the angle at which your toe is. The theta is when your foot is flat on the floor, that is 0. And if you are a ballerina, you can make it 90 degrees.
Right.
A good ballerina. All right, so that's the angle that your ankle is making with the ground. All right, so coming back here, so there's the tendon. This component of the force gives you, this component has no torque. This component F, tendon cosine theta, times the moment arm, 20 centimeters, is equal to F joint, and again, there's theta again. This component of the force gives you a torque. This component of the torque doesn't give you a force. F joint times cosine theta, the moment arm is 15 centimeters. Okay, so the joint force is 20 divided by 15 times the tendon force. Cosine theta cancels. Okay. The joint force is 4/3 the force on the tendon. The force on the tendon was, you saw that the force on the tendon was 3 mg times 4/3 gives you 4 mg. Okay. The force on the joint, this force is 4 times your body weight. Okay. So your body has to bear all kinds of large forces. When you stand on tiptoe on one foot, the force on your tendon is 3 times your body weight. This is 3 times your body weight, and on your joint is 4 times your body weight. The force on this bone is 4 times your body weight. That's right. Okay. Again, this shows you all the details of the calculation, but you don't have to know that. All right, now what we're going to show you is the following. Let's say you're holding a dumbbell or you're holding a bowling ball, so like that. The weight of the bowling ball is trying to rotate this arm clockwise. And if your arm is at rest as you're preparing to bowl, this is trying to rotate it clockwise. Something has to rotate it counterclockwise. Okay, so this force on the tendon is rotating it counterclockwise. And what we'll show you in a second is if this weight is 100 pounds, well, let's not do 100 pounds. Let's say this weight is 10 pounds. This force is roughly 90 pounds. Okay, so to lift a 10-pound force, you're exerting a 90-pound force. It seems like a pretty bad design, right?
It seems like overcompensation, yeah,
So why do you think that is?
to prevent the tendons from snapping.
Mhm.
It's not for me because I have nubby limbs.
Mm.
It's
Mm.
not for me because I have little nubby limbs. Look,
Mm.
they're little.
Yeah, well, yeah. No, your muscles are as strong as anybody else's, so nubby limbs means you won't tear your tendons easily. So you're at an advantage.
You're at an advantage, not an effective donation.
Okay. Okay, so here's what's going on. So the input force times input distance is output force times output distance. Okay, this is the work you put in, and this is the work you get out. Okay, this is assuming there's no friction. So the input force is the force of the muscle, and since the muscle cannot contract too much, if you want to get a large amount of work, so this is the output force. If you want to lift it a large distance, if you want to get this large, since your muscles cannot contract much, this is small, the muscles have to bear large loads. So that's what's going on. Okay, that's why the design. So you're applying forces by using muscles, and they cannot contract too much. And that's what. Okay. All right. So let's look at this situation. Yep. Mhm.
So when I'm drinking beer, I'm doing 12-ounce curls, and it's actually exercise, is what you're saying.
Yeah, that's true. But the thing is,
I know, I'm just being a smart aleck, so.
no, I understand.
That's far more carbs than you're using up, though.
Right.
Yeah, so to remark, okay, so do you know how much energy this thing uses, this iPad? It's roughly 100 watts, meaning it's using 100 joules a second. Okay. Do you know how much energy your brain is using?
Well, when I drink beer, not much.
20 watts. 1/5 this. And your brain is 1,000,000,000 times more powerful than it. Let me say that again.
So it's about energy efficiency.
Oh, there you go. Thank you. Amazingly efficient. Did you hear that? Okay, this is a 20-watt device.
It's able to do more with less.
Yep. I mean, a lot more.
We're only using
Huh?
roughly 10% anyway.
Yeah. Wow, not even 10%.
Like 4%.
No. Well, anyway. Okay, it does all the background work. Okay. So your body is amazing. Yeah.
That's what I tell myself every time before I go to bed.
So you're
You're
saying
gonna
that
wake
the
up
design
just because
is
you
right,
exist.
Huh?
huh?
I said, you tell yourself that before you go to bed.
Okay.
Wake up in the morning, it's not a pain because you exist.
So
My
you're
body's
saying that the
amazing
design
now.
of our body is in order to use as little energy to do as much work.
Well, okay. So biology has had millions of years to perfect a design, and so when you find a solution in biology, it's a pretty darn good solution. No, not. Let me finish this. You've taken up your questions for today. Not for today, for 5 minutes. Okay. All right. All right, so we're going to calculate the force here. Okay. We're going to show you that to lift a 10-pound load, you're applying a 100-pound force. Okay. All right, so here's the model. Okay, here's your arm. There's the load. And so you can call it barbell or whatever. There's the load. And there's the force that the muscle exerts on this bone. Okay. So we'll take this as the pivot point. This force is rotating your arm clockwise. This force is rotating it counterclockwise. Okay, and clockwise torques are taken to be negative, counterclockwise torques are taken to be positive. Okay, so that's the convention. Okay. This torque is the force, the load you're lifting, times the moment arm, which is 35 centimeters. And since it's a clockwise torque, it's negative. The force of the barbell times 35. And this force, which is a counterclockwise torque, is positive. So force of the tendon times the moment arm. Moment arm is the distance you measure to the pivot point. It's 4. And so if you bring this over that side, and 35 divided by 4 is 8.75. So the force that the tendon is exerting is 9 times the load, or 10 times the load. Okay. All right, let me draw another diagram because I want to show something else to you guys. So there. This is the tendon force, and we'll call this the load force. Okay. And we'll call this X tendon and this X load. Okay, so this is a clockwise torque. Again, you don't have to know all the details of the calculation, you just need to know the results. Okay. And then if you're interested, you can always go back to the calculation. So this is a counterclockwise torque, which is positive. Ft, the force of the tendon, times the distance to the moment arm, minus the load times XL equal to 0. So FL, okay, so now I'm going to do a different calculation. I'm going to calculate the load. Okay? So you bring this to that side, and then which is XT times XL. All right, what does this equation say? This is the load that you're lifting. Okay, this is that distance. Now that distance cannot be changed, it's fixed for your body. Okay? This is the force that the tendon can bear. And there's a maximum force that the tendon can bear before it rips. Okay, so this, let's say this is the maximum. So now if you want to lift a heavy load, what do you have to do? If you want to lift a heavier and heavier load, this is fixed, this is fixed. The only thing you can do is you can decrease this. Put this load closer and closer to the joint. That's her advantage with stubby arms. You know? So you reduce this, you can lift heavier and heavier loads. Did you guys understand that? That's what's happening here. See, these guys are lifting a heavy load, and the way they lift that load is they're putting the load very close to the joint. They couldn't lift this if they were holding that in their hands. The only way they're lifting this is by putting it there, close to the elbow. Did you guys understand that? Okay, so they lifted that heavy load by decreasing this.
So I'm at the disadvantage.
With that?
So I'm-
Yeah, you're. Yep. You made a mistake, my friend. Yep.
So I don't understand, I do understand, but, like, when you're using like a fulcrum, like, further distance, you know, giving yourself more ample space for which the load to bear seems, that's what I've always been taught, so I would
Okay.
have thought something similar would apply with the
So,
human body, you know?
no, so there, the fulcrum is here, the load is here, and you're applying a force here. The arm is large. So the further you are, when you apply a force, you want to be far from the fulcrum. That's what a large wrench does. Okay.
Yeah, because what he's saying is that our torque is actually here, because this is where the tendon is. You can't put the torque here, because it's the tendon that's actually moving it, so you have to put whatever it is.
Yeah, no, I'm
closer to
putting
that.
closer shortens the fulcrum, whereas when you're using like a stick to lift a heavy instrument,
Okay, so
the
here-
further out you are on the stick, the more you have to push to make the object move.
Okay, so here's your thing. So here you're lifting this thing, but this is the force you're applying, okay? The force you're applying and the load. You can lift a large load because this distance is smaller and this distance is large.
Oh, okay.
And the larger this stick is, the smaller the force you'll apply. Okay? So again, the torque is force times the moment arm. Okay, it's force times distance. If this is large, then you have to apply a smaller force. It's as simple as that. Okay. All right. So the point of all this was to show you that there are large forces that are applied in your bodies. Okay, that your bodies apply, and also to be smart about stuff. So, for instance, I mean, this is okay. So. Again, so something like that, if you analyze it, it becomes clear, okay? So if you want to lift a heavy load, what you want is you want to reduce this distance, okay? So put the load closer to the joint and the heavier load you can lift, okay? So if this distance is reduced by a factor of a half, you can lift twice the load. Instead of 100 pounds, instead of 1,000 pounds, you can lift 2,000 pounds. Okay, so that's the idea. All right. So machines have a mechanical advantage. All machines have mechanical advantage. Mechanical advantage is output force divided by input force. Okay? How much force did you lift? How much load did you lift? And what did you have to put in? That's the mechanical advantage. Now, most machines have mechanical advantages of 3, 4, or whatever, numbers bigger than, meaning you can lift a load of 4 times the load for an input force of 1/4. Okay, so here, this is your input force, and this is the load you're lifting. Your mechanical advantage is 1/10 almost. You're applying a force 10 times greater than that. And again, like I said, the reason you're doing that is because your muscles can contract only a little amount. Okay? And so that's why you do this. Okay, so here's a device that will help you lift a heavy load, okay, by making the load closer to the joint. Okay, now let's look at the forces in your jaw. Okay, most of you know this, that your upper jaw cannot move. It's only the lower jaw that moves up and down. Okay? And this muscle lifts the jaw up and down. Okay, so well, this muscle will lift it up, and then you have to have another muscle to bring it down. Okay, so why is that? Muscles can only contract. Okay, so this muscle lifts up, and there'll be another muscle to bring it down. But anyway, so there is the pivot point. And here's an amazing fact. Okay, so when this muscle contracts, this jaw pushes again the upper jaw, and the upper jaw will push down on your teeth. It pushes down on all the teeth. It'll push down on this teeth. And the force on this teeth that this upper teeth applies on this lower jaw is 1,200 newtons. Do you have any idea how that is? That large?
Seems like it.
That's twice your body weight. Twice your body weight.
I know that like the jaw power of like some animals is much stronger than humans, but they can crush bone with their jaws. So that must put a lot of force out. You know.
Yep. So this force is twice your body weight. Okay. All right. You learned that the muscles can apply a large force. Okay. And so the reason this force is large is because you see it's almost as close to the pivot point as the muscle force. Okay. So what this says is, in this diagram, if this is 5 centimeters, this is 5 centimeters, this is 7 centimeters. So the bite force is 5/7 the muscle force. And this is almost 1. So it's as large as the muscle force. Okay. So again, let's say we'll call this X muscle. oops, let me write it. So this is X muscle, that's the distance, and this is X byte. Okay, so about this pivot point, the muscle force is rotating it clockwise, so it's minus muscle force X muscle, and about this pivot point, the byte force is rotating the lower jaw counterclockwise. And so the byte force is xm over x byte times the muscle force. You know muscles can exert large forces, and if you want a large byte force, you want this to be close to 1. Okay? 1 is the smallest you can have. You can't have this, your teeth behind the muscle. Okay? So, well, you would lose distance. Okay? So you want a large byte force. What you want is this to be as small as possible. Okay? So you want to be as close to the pivot point as possible. The larger this is, the smaller this will be. Okay? So here's a cat. That distance is large. The byte force, X muscle, X byte muscle. So for the cat too, the muscle force is large. So since this distance is large, the byte force is small. A cat is a predator. Why is it going with a less byte force?
It's less force to cut than it does to crush.
Hmm?
It takes less force to cut than it does to crush.
Yeah, so this thing, okay, that's part of the reason. See, this has a large force, but you see there's not much room here. So your teeth cannot gain enough velocity. You're not slashing or anything. You're just worried about crushing. Here, with a wider mouth open, their jaws can move faster. They can pierce things, and they don't want to crush. They just want to pierce and cut stuff. And so
They have the speed because of the
very,
motion.
yep. So what they are looking for is speed, and for the range of motion, they're willing to give up byte force. Okay, so that's what's going on.
Sounds like they just don't need it, byte force to be as high.
Right. So you just want to rip into the jugular. Yep. The smaller byte force is compensated for by teeth that are much sharper than ours. The canine teeth have a wide range of motion. Dogs and cats can open their mouth much wider than we can, and are well adapted for rapid slashing bites. Okay. So your design is based on your needs, okay? And your design evolves to best suit your needs, okay? And again, if you want a good solution to any problem, where is it that you go?
Biology.
Biology. That's where the best engineering solutions are, okay? All right, so you saw that a wide range of motion. For that, you're giving up byte force. Okay? So you're compensating by less byte force. Okay, now we'll come to a different subject, elasticity and deformation. Okay, so for instance, okay, you can take any object, a bone, any object, metal, you apply a force and you will deform it a little. Okay? If this was a rubber band, for the same force, you would deform it much more. If it's a steel rod, you deform it less. Okay? So for instance, this shows you, okay, this is the force you've applied, and this is the stretch. That's the stretch. For a steel rod, they give you the numbers. For a 1 meter long steel rod, 1 meter long is about this long. and 1 centimeter diameter. 1 centimeter diameter is that much. So it's a thick steel rod. It takes a force of 16,000 newtons to stretch the rod by 1 millimeter. 1 millimeter is that much. 16,000 newtons is about the weight of 20 people, 25 people. So 25 people would have to hang on to that steel rod to stretch it by 1 millimeter. Okay? So the slope is something called the Hooke's constant, and the stiffer the material, the higher the slope. The less for rubber, the slope would be very small. Okay? So, and rubber would stretch more. Okay? So we'll remember that. Okay? So now that's what we're looking at. Okay, so here's this object, you apply a force and it stretches. What will happen when you remove the force?
Bounces back.
It bounces back. Okay? So when you walk, your bones compress, and when you lift off the weight, your bones go back to the original shape. How many times do you want your bones to do that?
Till the day you die.
Till the day you die, millions of times. You want elastic behavior. Okay? You have a suspension bridge. Every time you drive by, these cables stretch. After your car is gone, what do you want the cable to do? Retract, go back to its original shape. If it didn't, then before long the bridge would sag and it would be at water level. Okay? So you want materials to exhibit elastic behavior. When your heart pumps, what happens to your blood vessels? They stretch. And after the beat is gone, you want the blood vessel to go back. Okay? If your blood vessels didn't stretch, if they become stiff, then the pressure is high. Your heart would have to work harder. Okay? That's arteriosclerosis. Okay? But you don't want it to be too soft, because if it's too soft and it expands too much and bursts, that's an aneurysm. Okay? You don't want that happening. So you want your blood vessels to stretch and then become stiffer after a while. Okay? So you want the properties to change depending on how much stretch you have. Okay, so we'll see all of that. Okay, so elastic, you see elasticity everywhere. No object is perfectly rigid. Real objects undergo deformation in response to applied forces. Okay. Stiff materials would deform less. Pliant materials would deform more. Okay. Most biological materials deform considerably more than metals when subject to forces. Yeah. Your arteries flex with the pressure of each heartbeat. Bones withstand impacts and deform in process. Okay. So when you're standing, so right now my bones are compressed less. Now they compress more. Now they compress even more. Okay. But I'm happy they went back to their original shape. Nearly all biomaterials are elastic, and they deform to applied forces. Okay, deformation is often functional, storing energy for later use, or providing a way to dissipate energy. Okay. So here is the basis for how your muscles contract. Okay. Actin and myosin are proteins that work together to produce movements in all types of muscles. Okay, remember, muscles can only contract. Okay, so there's the myosin protein, and here's the actin protein. Okay, so here's this complex in the relaxed state, and here's that complex in the contracted state. You see, this distance is reduced. That's the small contraction. Okay, so let's see how this contraction happens. Okay, so you see here is a spring-like structure called titin. Okay, what the myosin molecule does is it uses ATP molecules and it compresses this spring. When these springs compress, the two actin molecules come together. So that's how your muscles contract. Okay, so myosin acts as a molecular motor. Okay, what does a motor do? It converts energy to motion. Okay, using energy from ATP to pull actin filaments together. And how does it pull it together? By compressing that spring, okay, causing them to slide past each other. So this model is known as the sliding filament model, okay, and it's the basis for muscle contraction. Okay. All right, so you apply stress to this object and it strains, okay? And like I said, the stiffer the material, the higher the slope, okay? So the amount of force you need to apply is this constant K, which depends on the material, and stiffer the material, bigger K is, and this is the amount of stretch. The bigger this is for a given force, the smaller will be the stretch. So for rubber, K is very small. For steel, K is very large. Okay? This is called the Hooke's law. Rigid objects have very large values of K. Okay? Objects with small K are pliant material, are called pliant material. Okay? Now here's the deal. This K depends on the dimensions of this object. So it depends on the area of cross-section and so on, and the length. So we want to come up with something that is not dependent on the dimensions of the material, but depends just on the material. So we want the material property. And so if you divide this force by the area of cross-section, and if you divide the stretch by the length of the rod, if you divide that, then this number only depends on the material. It doesn't depend on the dimensions of the structure. Material property. Okay. And this is called the Young's modulus. Okay. So again, just like this guy, this for stiffer material, this number is bigger. And this number is bigger for steel than for rubber. Can you think of a material for which this is bigger than steel? What material is stiffer than steel?
Cobalt.
Titanium that you use a lot, okay, and so on. Anyway, okay. So this is called stress. This is the Young's modulus. This is strain. Okay, you can think of this as just the force applied, and this is how much deformation that happened. Okay. All right. Y is called the Young's modulus. It's a property of the material. It characterizes a material's stiffness. Larger values indicating stiffer materials. Okay, so stiffer the material, bigger this number, less it will stretch for a given stress. Okay, so here's Young's modulus for steel, structural steel. All this is multiplied by 1,000,000. We'll talk about spider silk. You guys have heard that spider silk is the strongest steel? Yeah. So you see Young's modulus is 20 times smaller. See, 200,000, 10,000, that's 20 times smaller. So what that means is if you apply a given force, the silk will stretch 20 times more than steel. But here's the number. Tensile strength tells you what force will break it. Tensile strength is the same. So while the silk will stretch more, it takes the same amount of force to break it.
Does that inherently make it stronger
Okay.
in a way because it has more ability to
Or elasticity.
handle?
No, well, it's the elasticity is for something else. Okay. So when a bug comes in, if it was too stiff, the bug would bounce back.
Right.
Yeah. Okay. So it's designed so that some of the energy is absorbed, it bounces, but you don't want to fling it back. Okay. Well, and also it all depends on, I imagine the structure, it depends on it's hydrogen bonding, which is weak bonding, and so it stretches easier. Yeah.
Oh, it has more than that.
Yeah. All right, so it easily stretches, but to break it, it takes the same amount of force. So again, when you do that, you're taking a silk rod and a steel rod of equal dimensions and then applying forces. Okay, so you apply force, it'll stretch this much and break, but this silk will stretch almost twice the length before it breaks. But the same force will break it. Okay? All right. Softer materials have smaller y. In general, biomaterials are softer. Okay. And here's another thing. Most material, we considered how most materials stretch, but your bones, you don't, in life, you don't experience stretching forces for your bones. You experience compressing forces. Okay? And it turns out that a structure, materials, is stronger under compression than under tension. Okay? So it takes larger force to break your bone by compressive forces like this. Bones and the structural elements in buildings are compressed. Okay? Concrete is often compressed, as in columns that support highway overpasses, but rarely stretched. Okay. This is called a shearing force. If you have a structure like this, you apply shearing force like that. If you apply two forces like this, see, it deforms like so. This layer is transported parallel to this layer. Okay. Do you know any structures that bear this kind of forces in your body?
A lot of your bones.
Huh?
A lot of your bones.
Your discs between your vertebrae. So when you lift like that, the discs have to bear these shearing forces. Okay, so you don't want to do damage to your discs. What's that?
Keep our back straight.
Yep. So when you, did we see this earlier, or we'll see this? Okay. So when you keep your back straight, what you're doing is you're using these muscles to lift your object. Okay.
Why don't you bend over here, keep your back straight so you don't.
That's what he does.
Yeah.
Mhm.
Hopefully you're using your muscles rather than your.
Yeah. All right, so here are shearing forces. Okay, so this is the force divided by this area. That's the shearing stress. This is the shear modulus. Bigger this number, stiffer the material, less it will deform, and this is the deformation. Delta L divided by T. Okay. So when you lift like this, you're applying shearing forces to your discs. You don't want to do that, so you want to lift this with a straight back. So you would apply compressive forces to your discs. Okay, when you're lifting like that, you're applying compressive forces. Okay, and that's better than applying shearing forces. Okay? Spinal traction is the opposite, pulling the vertebrae apart, and the discs are distracted, for example. Okay? Here is another force that you apply when playing sport, torsion forces. So if this disc is moving like that and that disc is moving like that, you're applying torsional forces. Okay. And again, the idea is you want to minimize damage. In sports, there are many examples. Okay. You apply torsional forces in twisting motion that can occur when one vertebrae is rotating on top of the one below it is lifting. Okay, so the stress can be minimal with good technique. Okay, so that's what coaching and good technique and all will do. Okay, so you're minimizing injuries. Right, this is the stress, this is the strain. Okay, the slope tells you how stiff a material is. That tells you bigger Y and bigger K, okay? So steel has bigger Y and bigger K. Rubber has smaller Y and smaller K, smaller slope, okay? This tells you how much you've stretched the rubber. So let's look at this graph. So you see, as you're stretching the rubber, after a certain point, it gets stiffer. Okay? And you might have experienced this. You can stretch a rubber band, it'll stretch, and then after a while, it gets harder to stretch. Okay? Look at steel. After you stretched a certain amount and it starts deforming, it becomes easier to stretch it. Okay? All right, what this graph tells you is if you stretch steel this much and then let go of the force, it'll go back to its original shape. So this is the elastic limit. This is the elastic limit for rubber. You stretch it this much and remove the force, it'll go back to its original shape. If you apply a force greater than that, steel will permanently deform, and this is the breaking point. Pretty soon it'll break. Rubber will permanently deform, and that's the breaking point. That's what these graphs tell you, okay? Any material will break if you pull too hard. The tensile stress that causes a material to rupture is called the tensile strength. So the force needed to break something is called its tensile strength. And that's what we saw. See, the tensile strength of steel and silk are the same. The force needed to break them are the same. Okay? So now let's understand this. Rubber is a polymer. In its relaxed state, the long chain molecules are folded and coiled. So the molecules are folded and coiled. And so when you're pulling on rubber, all you're doing is unfolding the coil, with only hydrogen bonds holding the polymers in the folded configuration. When you begin to stretch rubber, you're unfolding and uncoiling the polymer. So it's easy to stretch the rubber initially, okay? But once you've uncoiled the polymers, once the polymers in the rubber are uncoiled, further stretching requires lengthening the carbon-carbon bonds. That's much more difficult. And so it becomes stiffer and it's harder to stretch. Okay. So it takes no effort to start stretching rubber bands, but eventually the rubber band gets much stiffer and refuses to stretch further. Many biomaterials are polymers, and so they behave more like rubber than steel. So many biomaterials, you can stretch them easily initially, and then they'll get stiffer eventually. Okay, and that's a safety mechanism. You want your arteries to stretch initially, but you don't want them to stretch too much. Okay? So you have to have a safety net built in. Okay? So here's the biomaterial, the structure of biomaterials, especially the presence of long fibers, make them more complex than metals. Okay? So a tree, it's harder to stretch a tree, but you can bend it easily. Okay? All right, so here's steel and here's spider silk. You see the breaking points are the same. Okay, so the tensile strength are the same. Okay. Except that you see it's very hard to stretch steel. The Young's modulus, this slope is enormous compared to this. Okay, and when silk breaks, see the strain is 1. That means the length of that fiber has doubled. This strain is the change in length divided by length, okay? So the increase in length divided by length, that is 1. So meaning the length has doubled. When steel breaks, it's only stretched about 1%, okay? So you don't deform steel much, but you can deform spider silk quite a bit, but the strength is the same, okay? Suppose we take equal lengths of steel wire and dragline silk of equal cross-section and stretch them. The force and displacement of each until it breaks. The graph shows that the resulting stress-strain curves. Okay, so the breaking point is the same. Okay, again, the Young's modulus for spider silk is 20 times smaller. So for small forces, the silk will stretch 20 times more than silk will stretch. Okay? So let's say you apply a 10-pound force for a steel bar and a silk thread, same cross-section, same length. The silk will stretch 20 times more than the steel fiber. Okay? Okay, there is high tensile steel that is 3 times stronger. This is structural steel. Okay? So here's another amazing thing. To make steel, you have to melt iron, treat it to high temperatures, and so on. Treat it to thousands of degrees Celsius. Where is the silk made? Inside an insect at room temperature, at body temperature. And you're making something as strong as steel. Absolutely amazing. So for a natural product made at room temperature by spiders digesting small insects, the strength of silk is very impressive. Okay, so if you think of it from a process standpoint, pretty amazing. All right, let's take a steel rod and stretch it. Yeah. So this is the force, this is the change in length, okay? And it'll stretch. And when you let go of the force, what happens? It goes right back, okay? And so when you're stretching it, that is the path you're going in. So this is for a steel rod and a spring and so on. And it'll go right back. Okay, so when you're stretching it, that's the energy you're stored under it. The area under it is the energy you store. And when you go back, all the energy is given back. Okay? So this is true for a spring as well, for an ideal spring. You stretch the spring. Okay, so the force times change in length. Okay, this area is equal to energy. When you're stretching it, that's the energy stored. And if the spring comes right back along that curve, it'll give up all the energy. Okay, so the spring gives back 100% of the energy. If it comes back on a different path, you see it's giving back less energy. Okay, your tendons will come back almost along the same path. You guys remember how much energy your tendons give back? 90%. Mm-hmm. Silk, okay, so let's do, so here's your tendon, and then that's on the way up, and on the way down, your tendon will come back this way. This area is 90% of this area. Okay, your tendon gives back 90% of this area. Now, if you do this for silk, the silk comes back this way. For silk, this area is 35% of that area. Silk gives back only 35% of the energy. Why is that? You don't want your silk web, the spider web, to be like a trampoline. If it's like a trampoline, the bug comes and hits the web, it'll just bounce out. Your dinner has gone out the window. Okay? So silk wants to not give back all its energy. Okay? All right, so this is called a loading curve. This is an unloading curve. Okay? So there's the loading curve, there's the unloading curve. And this is designed deliberately. This is how much energy it gave back, and this is the energy that was stored in. Okay? Unlike an ideal spring, unlike an ideal spring whose unloading curve exactly retraces the loading curve, so for a spring, the loading and unloading curve are the same, meaning it'll give back 100% of the energy it's stored. unlike an ideal spring whose loading curve exactly retraces the loading curve, silk has a memory. You see, for silk, as you remove the force, see, its length is not decreasing. It stays stretched. And then eventually it will snap back. Okay. That is, a silk fiber initially retains nearly its full elongation, even though the pulling force is decreasing. The fiber snaps back only after the stress has been significantly reduced. Yeah. A stretch spring stores energy. An ideal spring gives back all the stored energy, okay, because the loading and unloading curve are the same. For a silk, you see the area under this curve is much less than that area. Spider silk has a resilience of about 0.35. That's the fraction of energy that is returned. So the silk gives back only 35% of the energy that is stored in it. What happens to the rest of the energy?
Gets spread out.
It gets turned into heat. Okay? So some biological structures need to store and then release energy, like tendons. Others, such as spider webs, need to dissipate energy, okay, so that they don't lose their dinner. Okay? So organisms have evolved biomaterials to suit their functions. Okay? So here's an artery. Okay, so artery is made. Your arteries are made of two things: collagen and elastin. Elastin is that background pink stuff that is soft and stretches like rubber. Okay, when your heart pumps blood, you want the arteries to expand. Okay, collagen is stiff material. So initially, see, the collagen fibers are folded. Initially, it'll stretch easily, but once it straightens out, collagen doesn't stretch easily. So initially, your arteries will stretch easily because the collagen is easily stretching and the elastin is easily stretching. But once that straightens out, now it's become stiffer. It's harder to stretch your arteries. Okay, so that's the protective mechanism. So you don't get aneurysms every time your heart beats. Okay? So that's design. So arteries need to be rather soft and elastic so that an expansion with each heartbeat can act as a shock absorber. At the same time, an artery can't be too elastic without having an increased risk of an aneurysm. Yeah. So everything is designed very well. Yeah. Artery walls have a complex structure. They're made of elastin and collagen. Elastin is that background rubbery material, and there's the collagen fibers. Collagen occurs in almost pure form in the tendons. Okay, so collagen tendons are made of collagen, and they are 0.9 resilient, meaning they give back 90% of the energy. Elastin is the body's rubber. It's soft, pliant, and easily stretched. Okay. The elastin allows an artery to expand to buffer increased pressure of a heart contraction, while the collagen provides a safety net that prevents runaway expansion. Okay? So once the collagen is stretched, it won't let your artery stretch more without greater forces. Your skin is a similar elastin-collagen composite. It's quite elastic in response to small stresses, but highly resistant to large deformations. Unfortunately, your skin loses its ability to produce elastin as we age. Wrinkles are a consequence of that, you know, if you have less elastin. Now we'll look at your bone. So your bone is something like this. So I'll draw a hollow cylinder. Okay, this stuff is solid. So the outer layer is solid, and that's what's structural. The inside stuff is soft matrix. That's where physiology happens. Blood cells are produced and all that. So this stuff is what provides support. That provides mechanical support. The spongy bone serves essential physiological functions, but contributes nothing to the mechanical properties. The mechanical properties of a bone can be modeled by that of a hollow cylinder. Okay. So this is dense and rigid compact bone. This is dense and rigid. Okay. So now we'll look at some of the forces. Okay. So here's a bone. A bone is stronger under compressive forces. So it's harder to break a bone under compressive forces. So if you apply forces like this to a bone, it takes greater force to break it than if you apply forces like this, tensile forces. Okay? In life, you never encounter tensile forces. Nobody's putting you in a rack and stretching you, at least not too often. But you do go run, walk, and stuff like that. You jump off walls. So you have to be designed to be stronger under these conditions. Yep.
So, as we put force on our bones, they become harder if they, because they realize, oh, we need this much density in order to, say an acrobat, do they begin to get like, more, do their joints become stronger, do their bones?
I think the muscles become stronger. I don't know if bone density increases.
Muscular support than anything with the bones.
Mm-hmm.
Unless you have an excess of testosterone, your bones aren't really gonna get any harder than they are.
Well, I mean, I just mean that they're,
The density of bones. Okay, so if you want to make a bone stronger, you have to make this thicker and denser. That outer hull, that portion thicker. In osteoporosis, this becomes thinner and your bones become weaker. Yep.
So if you're standing and you're hit by something that
Mhm.
breaks your bone,
Mm-hmm.
it's harder to break the bone because you're standing, you're applying force to both the top and the bottom of it. Whereas if you were laying down and you were hit by something, your bone might break easier because there's
So
more force on it.
let's talk about breaking bones. Okay, let's break bones. All right, so a bone, okay, again, the strength is coming from this thick walls. A bone is stronger under compressive forces than tensile forces. Okay, if you could stretch a bone, it's easier to break than compressive forces. Okay? So it's weaker under tensile stress. Okay, so here's a bone. If you apply force sideways, look what's happening. As the bone is bending, see this side is being stretched. That's undergoing tensile stress. This side is being compressed. So this is how bones work. When you apply a sideways force like this, it will crack on this side. So that side of the cylinder will crack. Okay, now let's take a rubber band, stretch it. If you let go of the rubber band, all the energy is given back. Okay? When the rubber band breaks, what happens? The broken pieces, they fly. All the energy has to be released. Okay, so just like that, when this guy was stretched, it was like a spring. When it cracked, all that energy released, will break other parts of the bone. So the crack propagates. Okay? If a bone is bent far enough, it will fail on the outside edge of the bend when the stress at the outer edge reaches the tensile strength. Tensile strength is stretching strength. Okay? The energy released when the stress bone breaks then drives a crack, a bone fracture, well into or even through the bone. Okay. So the sideways force cracks the far end. Okay. Now let me show you a couple of numbers. Okay, so what we're going to do is, okay, so you have plenty of room for safety. Okay, so we'll look at, so again, what is the bone? It's a hollow cylinder, and the thicker the pipe, thicker the walls, the stronger your bones will be. Okay? So what we're going to do is the compressive strength of a compact bone. So this is the compressive strength of a compact bone. Okay? This is the force you need to break it. Okay? Somewhat greater than tensile strength. Okay, so we're going to get an 85 kg, 190-pound man to stand on one leg. going to get a 190-pound man to stand on one leg. And what has happened to the bone? It's compressed. Okay? So let's calculate what is the stress on the bones. So this is what is needed to break it. So what this shows you is this area is what it's calculating, the outer area minus the inner area. Okay? So it's calculating this area. That's the area. The stress is the weight divided by the area. There's the weight, mg divided by that. There is that compressive stress. So when a man is standing on one foot, there is the compressive force, and the compressive strength is that. So when you're standing, you're applying only 1.5% of the weight that's needed to break the bone. Plenty of room. Okay? So that's what that number is. Yeah. You're only applying 1% of the stress that's needed to break the bone. Okay, now let's go for a run. Okay? All right, well, before we go for a run, let's calculate. This is the strain. That's the amount of compression in the bone divided by the length. Okay, and so there is the stress. There's the Young's modulus for bone. You can put that. And there is the strain. And this, the length times this number gives you how much the bone compressed. So this is when you're standing on one leg. This is how much your bone compressed. 600th of a millimeter. That's the width of a hair. Pretty strong bone. Okay, so plenty of room for error. Okay, that's about the diameter of a human hair. An increase in stress by a factor of 7 while running. So when you're running, you're increasing the stress on the bone by a factor of 7 to 10. When you hit the floor, you have to be stopped. You know, your whole body lands on that. You have to be stopped. So the stress on the bone increased by a factor of 7 to 10. And the compression will increase by a factor of 7. So 7 times that is 42.5. So now your bone is compressed 0.5 millimeter. Okay. Every time you land on your foot when you're running, your bone is compressed 0.5 millimeter. The stress was, when you were standing, it was 1%. 7 times that, that's 10%. So even when you're running, the compressive stresses are only 10% of what's needed to break your bone. Okay? So if you want to break your bone, maybe you have to jump from a height like that. Yep.
So again, if you're standing and somebody's swinging a pipe,
Mm-hmm.
is the fact that you're standing making your bone so it's compressed, is it a little less likely to break if somebody hits it with a pipe
Mm-hmm.
versus, like, let's say you're laying down and somebody hits you with the pipe? Does the compression from standing have anything to do to help?
Yeah,
strengthen the
it'll when you're laying down, it'll break easier.
Okay, I was just curious if the compression was enough to help.
Yeah, and that's what they do. In fact, when they build these bridges, what they do is, we heard of pre-stressed concrete. Okay, so what they do is they'll take a steel rod, put it in a vise, stretch this, lay concrete on top of it. Once this cures, they let go of this force, and so this concrete is compressed, and it's stronger. Same thing, like you said. Okay. Very neat. Okay. All right. So you see, when you're running, your bones compress about 0.5 millimeter. Okay. So in osteoporosis, okay, your strength of your bone comes from the thickness of the walls. Okay. Now here's the amazing thing about your bones. Okay. If you've seen bridges, if the columns develop crack, what happens?
It weakens the whole structure.
It weakens the whole structure. Eventually the bridge will fall. You can't fix it like where it is. Okay. If the cracks are inside, you can't scoop out portions of the column and then put new concrete on there. Your bone is constantly relaying new bone. The microarchitecture of the bone is constantly being recycled to maintain strength. So your bone, I don't know the timeline, but 10 years from now, that bone is totally new. So, okay. So what has to happen is you're removing bone, removing bone and laying new bone. Okay. Now, when you're healthy, that balance is there. In osteoporosis, you're removing bone and you're not laying as much bone. So that's how your bones weaken. Okay. So the microarchitecture of the bone is constantly being recycled to maintain maximum strength. This recycling is facilitated by bone cells that resorb all bone. You resorb, and bone cells that build new bone. Okay, so here some cells are absorbing bones and other cells are relaying bone. As you get older, this homeostasis favors the cells that resorb the bone. As you get older, these guys are doing their job, but these guys are not doing their job. Yep. You got to fire them. Yep. It affects women more than men. Okay.
Is that goddamn lack of estrogen after menopause?
That's right.